Hi, my name is Brian, and I'm going to be talking about the Bohr effect. And so when you think about the Bohr effect, this equation might come into your mind. And so we have carbon dioxide, water, carbonic acid, hydrogen ions, as well as bicarbonate. And we've learned in this class that bicarbonate is a great buffer in your blood. And so when you think about this equation, a great way to attack this problem is really considering how it affects our body. And so let's focus on CO2. Well, when someone's hyperventilating, you also have to consider that CO2 levels decrease because of the increase in oxygen that's being introduced in their body. And so a good way to think about it is that CO2, if CO2 levels are high, oxygen levels are low. And so if someone's hyperventilating, we can expect that CO2 levels would decrease because of the increase in oxygen. And so if that's the case, you can also assume that hydrogen levels decrease based on Le Chatelier's principle. And so based on this idea, we can understand that an increase in oxygen decreases carbon dioxide saturation, which then affects our hydrogen ions. And a good idea to think about hydrogen ions is that the decrease in hydrogen can also be associated with pH increasing. And this increase in pH really affects our body. And a condition in which our body actually increases in pH is considered alkalosis. And so alkalosis, which is the increase in pH, affects our body. And let's say the opposite is also true, where in the sense that instead of hyperventilating, someone were to increase or breathe into a bag. And so breathing into a bag would recycle that carbon dioxide that someone's breathing out. And so therefore, if we were to deal with another example, for example, increase in CO2, you would expect an increase in hydrogen ions, again, based on Le Chatelier's principle. And if that's were the case, you would expect pH levels to decrease. And this decrease in pH is really associated with another condition called acidosis. And so this Bohr effect is a great idea in which the idea that CO2 levels really dictate how your pH changes in your body. And now we will use that understanding to associate this on how it can affect hemoglobin in terms of saturating oxygen or picking up oxygen. And so based on our understanding of the Bohr effect, we can now apply it to how hemoglobin might interact with it. And so let's say hypothetically we have a muscle in which right after we work out, we can expect an accumulation of lactic acid. And so the whole idea of accumulation of lactic acid is because it enters lactic acid fermentation. Okay? And so lactic acid fermentation, it doesn't have oxygen. And so this lactic acid fermentation decreases the pH because of it being an acid, and therefore increases the hydrogen ion. And these two go hand in hand. And so let's imagine how this change in pH or this increase in hydrogen ion affects hemoglobin. And so let's say we have a hemoglobin. So let's say, and hemoglobin, as we know, is a quaternary structure that consists of 4 subunits. And so these subunits, each subunit has a histidine residue as well as an aspartate residue. And aspartate, as we know, is naturally negatively charged. And so now we have to consider histidine, which is relatively neutral in the pH of 7. And so therefore, how does this change in pH affect histidine? And so this increase in hydrogen ions really affects histidine in the sense that it can become protonated. And this protonated gives histidine a positive charge. And because of this positive charge, you can expect this negative charge to interact with it. And so therefore, there is this electrostatic interaction. And so now we have to take a step back and think about what happens to my hemoglobin. And so hemoglobin, its job is to pick up oxygen. And so anything that were to change that, the structure of hemoglobin would change its function. And so because of this interaction between aspartate and histidine, this electrostatic interaction really interferes with the structure. And so let's say that this hemoglobin is oxygenated. It has an oxygen on it. And so let's say it's holding multiple oxygens. And because it's holding multiple oxygens, this change in structures really interferes with how it's able to hold on to oxygen. And so therefore, you can expect these oxygens to release. And so this release in oxygen, therefore, changes it from being an R state to a T state hemoglobin. And now let's think back to how lactic acid came about. The lactic acid accumulated because of the fermentation, which means the lack of oxygen. And so because of that, the hemoglobin, or the myoglobin actually, the myoglobin in the muscles need oxygen. And so this whole idea of this electrostatic interaction releases the oxygen in the hemoglobin, and you can expect the myoglobin here to receive this oxygen. And so that makes sense in the sense that hemoglobin is traveling all around your blood, or around your body, through your blood. And this hemoglobin reaches this area where lactic acid fermentation is accumulating. And so therefore, the decrease in pH allows things like histidine to become protonated. And because of this protonation of histidine and this aspartate that just happens to interact with each other, this interaction, which is the electrostatic interaction, causes the oxygen in these two subunits to release. And since we are talking about the muscle's myoglobin picks up the oxygen that's being released on this hemoglobin that just happens to be in the area. And so that makes sense because the thing is, this myoglobin wants oxygen because of the muscle that just went through fermentation. And so because of this interaction between the Bhor effect and hemoglobin can really decide on how, for example, hemoglobin goes from a T to R state, or in this case, R to T.